Inadvertently, I started this a little bit too early, but it's okay. We can kick this off a little bit early. Not a huge problem. We may have some people. Um, we'll back this up a bit. Okay, so it doesn't hurt anything to go back over something we've already done. And by that period of time, it will be actually 11 o'clock. So what we're doing, these are all covalent. If you notice, we're sharing electrons. And in this first example, right here we have each hydrogen has one proton and one electron. If you're looking at your periodic table, you will be able to tell that. The atomic number is 1, and then if you look over in the upper right of that little box, there'll be a little 1, and that tells us that we have one electron. So that first shell is only going to be stable if it has 2 electrons, and that would actually make it filled. But obviously it only has 1 electron, so it is not a stable shell. So the way to fill that, of course, is if we can bond 2 of these together. So we're sharing 1 electron from each hydrogen. Then what we're doing here is we're filling the first shell of both atoms involved. So both, because they are sharing those, both are going to have 2 electrons in that first shell, and of course that would be a filled outer shell. All right. Now, if you'll notice, so that is a single covalent. Anytime you're sharing, that's a covalent bond. When you're looking at oxygen, oxygen has a total of 8 protons. On the periodic table, you'll see that. The atomic number will be the big number in the upper left-hand corner. So it has 8 protons, and therefore it would have 8 electrons. 2 of those would go in the first shell, and that leaves 6 for the second shell. Obviously, that's not filled. The second shell needs 8 to be stable. So in order to make that stable, if you're working with 2 oxygens, the only way that will actually work is if you share 2 electrons from one oxygen here and 2 electrons from the other oxygen. So actually you're sharing 4 at this point. So this last shell, if you count that, you get 2, 4, and then these 4, that would be 8. And then for the other atom, 2, 4, and then the 4 in the center, which would be 8. So both of those now have filled out shells, and it is a stable molecule. It's not a compound because we don't have 2 different elements. So that's what you call a double covalent bond, and we've looked at these others, so I don't feel the need to go back through those. Here's water. We spent quite a bit of time with that. We're not finished with it by any stretch, but we'll come back to that for sure. Discussing water's properties, we'll get into that. Okay, and we have discussed this. Anytime you're working with covalent molecules, you would call that, if you're sharing electrons, you would call those molecules. Now, anytime you're working with molecules where you have 2 different elements, those are referred to as compounds, which that does sound a little picky, but nonetheless, you get 2 different elements bonded together. That is a compound. So even if they are covalently bonded, it is referred to as a compound. Most people would not be too horribly disturbed if you did call those molecules because they are covalently bonded. Not a problem. But you do have 2 different elements, so you could also call that a compound, which per this book, it looks like they would prefer you call those compounds. But again, I don't think that's really going to be a problem for most people. You could get somebody who's so picky about, you need to know exactly the way the book presents it, and that's what you have to do, then, that's what you do. I have been in those classes where the instructor is so incredibly picky, then, okay. It really depends on who wrote the book, They can pretty much write whatever they want to as long as they can get it published. And then who's teaching the class, and it's kind of their class. They can do whatever they want. So you're kind of juggling those two things. And I try to be real easy to get along with and make it so that it's really not such a complicated thing that everybody's like, oh my goodness, I have to do it this way. So you get two different elements. You can call it a compound, but if they are covalently bonded, personally I would call it a molecule. Compounds are typically refer to elements that are formed, or compounds that are formed by one atom losing one or more electrons and another atom gaining one or more electrons. And we did talk about that just briefly. But if you're looking at group 1A, all those in the very last shell, in their valence shell. So in order to fill up those valence shells, now we're going to work with all of them. Hydrogen, say lithium or sodium or potassium or any of the others, they have one electron in the valence shell. In order to fill up that valence shell, they would need to gain 7 electrons. Well, that's going to be pretty hard to do. What they could do is lose that one electron that they have in their last energy shell. And if they do that, if they lose that, then that energy doesn't exist. There's no energy shell if there's not an electron in it. So if you're looking at lithium, if you lose the electron in the last energy shell, then the first shell only has 2 electrons. Well, that's filled. All right, that makes lithium stable. Well, one electron that you're losing off of lithium, that could be passed to any of those elements that you have in group 7A. They all have 7 electrons in the last energy shell, valence shell. So they all just need 1. So, and we're not dealing with hydrogen, but the other elements in group 1A could lose 1 electron and pass it to any of the elements in group 7A. And then group 7A all would have 8 electrons in their last energy shell. So you could have lithium fluoride, lithium chromide, lithium bromide, or sodium fluoride, sodium chloride, sodium bromide, or potassium fluoride, potassium chloride, or potassium bromide. And again, it is a transfer. One loses an electron and one gains the electron. And when you do, that's what you call an ionic bond. And we have yet to really even get into it, but I keep referring back to that because I'm referring back to that. Because. Okay. All right. So let's go to nonpolar covalent bonds. Now, if there's no polarity to it, what you're working with is something that your electrons are shared equally between the protons. Okay. So given that, let's say if you're working with hydrogen, you have 1 proton, you don't have any neutrons, and you have 1 electron. All right. That electron is spinning and is at an equal distance from this proton. No matter where, is going to travel at an equal distance. Okay, so then if we were to share that 1 electron with an electron from a different hydrogen, so we have 1 proton and 1 electron, then those 2 electrons are shared equally between this proton and this proton. So what you really have here, you have 1 positive charge, you have 2 negative charge, and then you have positive charge. So all of those charges cancel out because they're held equally, the electrons are held equally distant from this proton and also from the other proton. So the charges are just basically cancel each other. So that is nonpolar. You don't have any polarity. Yesterday we looked at a situation where you had oxygen, and oxygen is electronegative, and it tends to pull the electrons from the hydrogen and pull them closer to the oxygen, giving the oxygen a partial negative charge because the electron spin, they get into this, what you would refer to as an elliptical orbit, and I'll just draw that. So the electron would go like this, like that. Okay, so that electron is spending a great deal of time near that oxygen. And keep in mind, with what we did with just one hydrogen, you had the one proton and you had the one electron. Normally that electron is going to orbit that proton at an equal distance from that proton. But if you get it near the oxygen, it goes into an elliptical orbit. So that means for a great deal of the time, that electron is pulled to the oxygen, leaving the oxygen with a partial negative charge, and both hydrogens would do that. So I guess I should show that with both hydrogens instead of just one. But, so what we end up getting is oxygen with a partial negative charge. Each hydrogen, since the electron spends a good deal of its time that direction, then have a partial positive charge. And this is incredibly significant. And this is one of your discussion questions. Why is water polar? Water's polar because oxygen is electronegative, and it tends to draw the hydrogen's electron, the electron that is on hydrogen, away from hydrogen closer to the oxygen. That's what oxygen is. It acts like an electron magnet. It pulls hydrogen's electron, there's only one, closer to the oxygen. Well, obviously that will make the oxygen partially negative, and then it will leave the hydrogens partially positive. So you get this polarity. You get basically a bar magnet where you have one end of it has not a complete negative charge, but a partially negative, and the other end of the molecule where the hydrogens are have a partial positive charge. So it is certainly going to be polar. Anything where you got positive, negative, you've got polarity. And really anything that has oxygen is going to be polar. And if you look at your periodic chart, the way to look at electronegativity is the element that has the strongest electronegativity, the strongest pull for electrons, is fluorine. Now that's group 7A period 2. So that's fluorine, the strongest pull of electrons. Okay, well that's the strongest pull, the strongest electronegativity. Well, look at where oxygen is. It's sitting right next to it, which means it has a pretty darn strong pull for electrons. And sulfur is very close to fluorine, and chlorine is very close to fluorine. So those are all electronegative. And another way to view this is if you start at the periodic chart in the lower left-hand corner of that chart, you have francium. That has the least electronegativity on the periodic table, so that one is not going to attract electrons at all. But if you go diagonally from francium up to fluorine, what you're doing is you're going from the least electronegativity to the greatest electronegativity, and that's the way the electronegativity increases, is from the lower left-hand corner to the upper right-hand corner. We've already mentioned noble gases. They're already stable. They're not going to attract electrons whatsoever, so we don't consider that particular column. But so electronegativity does increase when you go to the upper right of that chart. So anytime you're working with a compound that has fluorine in it, or chlorine in it, or sulfur in it, or oxygen in it, or nitrogen in it, or phosphorus, or bromine, you're working with some, those elements are all going to be somewhat, if not very strongly, electronegative. So they're going to be pulling electrons toward themselves, which was going to make them more negative. And wherever they're pulling them from, whatever atom they're going to get that electron, they're going to pull that electron from, is going to be partially positive. So any of those are going to lead to polarity. So you can just look at a chemical formula like H2S, and you know that, which is hydrogen sulfide, which is very poisonous, but you know that molecule is going to be polar, like H2O. Instead of oxygen, we're using sulfur, but it's very close to that fluorine, so that means it's going to be electronegative. So H2S is going to have polarity to it. So anytime you're working with the elements in the upper right-hand corner, you know you're going to be dealing with a polar molecule just automatically. It's very, very simple at that to recognize that. If you understand in the upper right-hand corner, you're dealing with some very electronegative elements. So they do pull the electrons that direction towards that element, away from the other element, therefore leaving the other element partially positive. And that's electronegativity. Very important, because eventually we get into the point where we have molecules interacting with molecules. Well, then you have to understand, well, which part of the molecule is going to be, does it have any polarity, or is it completely nonpolar? You know, like the hydrogen sharing the electrons with another hydrogen. That's nonpolar, completely nonpolar. So if you have something completely nonpolar, then water's very polar. So let's say that you put oil in water. Oil is nonpolar. It's not going to mix with water. So anything that has polarity to it will mix with water. So you can just automatically, knowing that, you can automatically go, okay, well, I know what has polarity. What dissolves in water? Sugar. It's got to have a lot of polarity to it, because water's polar. Sugar must be polar. Sugar dissolves in water. So, you know, like dissolves like. So if you have a polar substance like water, then anything that is polar will dissolve in that. Salt must be very polar. It dissolves in water. So, you know, some of you may be, and I used to do this, I'm not currently doing this, but I need to do this, is go back to the weight room to try to get some mass on my body. But I haven't made my way back into the weight room. I will. I keep telling myself, if I could just get up an hour earlier, and I could go to the weight room, and then you know, in 30 years, I would be all bulky. It would take 30 years. I'd be a 87-year-old man, but I would be hot. Yeah. Well, from the neck down, maybe. It wouldn't. Nothing would sag. From the neck up, it would all be saggy. Unless I had facelift, and I'm not opposed to that at all. No, my brother has had a facelift. He's even had a chin implant and cheek implant and hair implant, and a nose remodel and facelift, and I call him my sister now. I don't call him my brother. Yeah. How's it going, girlfriend? You okay? Everything happening in your world okay? Yeah. You still looking pretty? I like to give him a hard time. Very educated man, you know, very, very well educated. Has a master's in business finance. He's vice president of Wells Fargo, if that tells you anything, probably the largest bank in America. And he works in LA, if that tells you anything. And he also has a law degree. So anytime I can nudge him a little bit, I like to do that, you know, kind of bother him, which I can do that so easily. I can make him cry in 10 minutes. You know, I'm the only person on the planet that can do that. And I love to just twist him till he's like, no, Mom, make him stop. I don't know. I'm just mean that way. And I'm not particularly mean, but I am with him. You know, I just want him to grow a pair, you know. Just stand up, be a man, just grow a pair, you know. Tell me to get lost, you know. Don't put up with that. Well, don't let it affect you. What? You know. No, he's an older brother. You know, but I used to beat him up. I could always beat him up. When I was a kid, I would always beat him up. You know, and I always had all these friends on the block, and we'd play, and he'd come up, and he'd go, "What are y'all playing?" And I'd just go, "Get away! You're not playing. You're not part of this group. Go find somebody to play with." You know, I was horrible. I have yet to apologize. Okay. I'm still not apologizing. Just send him a copy of this recording. No, I still don't apologize. Grow a pair. And then we'll talk. Till then, no. Forget it. Okay. So again, going back to this polarity, the polarity thing is, you know, anytime you got something electronegative, you're going to have electrons pull that direction, if not completely off. You know, if you're dealing with, say, fluorine, fluorine is the most electronegative element on the planet, which means it will not just pull the electron closer from another element to fluorine, it will completely strip that electron completely off and hold on to it. It's kind of like chlorine. Chlorine is very strongly electronegative. If you put sodium, which only has one electron in its very last shell, the valence shell, chlorine it is such a strong electronegative element, it will just take that electron and grab a hold of it. It will pull it completely off of sodium. So, and it will grab a hold of it and keep it. Okay. So electronegativity is, you know, you could create where you actually, one atom loses an electron and the other atom gains. Why does one atom lose? Well, evidently the atom that's pulling that electron off must be very strongly electronegative. It just strips it off, just grabs a hold of it and hangs on to it, just pulls it completely away, not just closer to it, but completely away. And that's where you get into ionic bonding. So, you know, the whole concept of bonding is, you know, you get a little bit of, you get no pull whatsoever, or you get a little bit of a pull, or a little bit stronger pull, or you get such a strong pull, it will just grab that electron and pull it completely off. That's a very strong electronegative element. And like I said, going back to that chart, the closer you get to the upper right, electronegativity increases. So that helps you to understand bonding a little bit. You know, it's not like, well, you just don't have where you share electrons and you have a situation where one loses an electron and one gains. They call that ionic bonding. It's not that simple. You know, it's you've got a whole range of pull from no pull between the elements to such a strong pull that you completely strip the electron completely off, and you have everything in between. A little bit of pull, or a little bit stronger pull, or a little bit stronger pull, or you strip it completely. That's bonding, you know. And if you can think about bonding in those terms, then you totally understand. You know, you have a pretty good idea of how all that works. Looks like they're barbecuing out there. I don't remember the invite. You got an email? Oh, it's for students only. I know. We didn't get an email on that. Yeah, they're doing, you know, I don't know what it is. They're barbecuing. They got a, yeah. Well, maybe you can finish that lab test in about 10 minutes, then you can run over there and get yourself a hot dog or whatever they're passing out over there. Okay, so now we're getting at the point where we're dealing with such strong electronegative elements that they are stripping the electrons completely off of the atom and keeping it. So, for example, the easiest thing to draw, if we wanted to actually draw this thing as a Bohr diagram, let's do lithium, and we'll take that one electron. Now, lithium has 3 protons. It has 4 neutrons. How do I know that? Average mass is 7 atomic mass units. All right. If you look at that on the chart, it says 6.941. Round it to the nearest whole number. That's 7. So we know the 3. That's in the upper Left-hand corner, that's the atomic number. We know we have 3 protons. We know we have 3 electrons. The total mass is 7. 3 plus what would give me 7. Obviously, we have 4 neutrons. Okay, so, and then if we have 3 electrons, 2 of those we can place in the first energy shell, and then that would leave me 1 more for the second energy shell. Now, what I'm going to do is I'm going to bond that with fluorine. All right, so fluorine, group 7A, period 2. So fluorine has 9 protons, 10 neutrons. So I have 9 electrons. It gives me 2 for the first shell, and that would give me 7, 1, 2, 7 for the second shell. Now, I've already mentioned that if you're dealing with fluorine, that is the strongest electronegative element on the planet. It is so strongly electronegative that it will pull that electron off of lithium, and then that electron will then completely reside with fluorine. It is no longer found on the lithium. So this is obviously lithium right here. Okay, so that energy shell, the second shell of lithium, no longer exists. It only is there if you have something something in it. If you don't have anything in there, there is no shell. So the first shell of lithium has 2 electrons. It's filled, and then if you go over here to fluorine, fluorine has 8 in its last energy shell. The valence shell has 8. It's filled. So the second shell is filled with 8. For fluorine, the first shell on lithium is filled with 2. It's a stable compound. You've got lithium fluoride. And if you look at that, then what you also need to consider is we've kind of messed with the charges on this thing because it's not the same anymore. Lithium has 3 positive protons, and now it only has 2 negative electrons. I took one of them off. I had 3 positives and 3 negatives. 3 protons, 3 negative electrons. That's what you started with. Number of protons and the number of electrons will always be the same on the chart. Well, we're talking about nature now. We just lost an electron. So I have 3 positives and only 2 negatives. So 3 positives and 2 negatives. Well, a positive and a negative will cancel. That's neutral. Positive and negative cancel. That's neutral. So this lithium carries with it a positive charge. You could put a +1 there. It goes in the upper right-hand corner. Usually if you just have a plus, that just means +1. If you want to write the 1, you're welcome to. And then fluorine, I have 9 positives and I have 10 negatives. So we could do 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are all positives, supposedly. All right, positives. And then I have 10 negatives. 1, 2, 3, 4, 5. 10 negatives. Of course, all of the positives and the negatives cancel. That leaves me with an extra negative. So that atom now has a negative charge. Anything that has a charge on it is what we refer to as an ion. An ion could either be positive or it could be negative. Positive or negative. However, if you have a positive ion, like lithium, that's a positive ion, we call that a cation, specifically, cation. I happen to like cats, except for one of my cats. I've never found a cat I really didn't particularly just think the world of until I got this one. And she is so needy. She's so needy. She like meows all the time, and she wants to be in your lap all the time, and she just meows all the time, and she just needs your attention 24/7. She wants your attention so badly. When you go to sleep, she wants to sleep on top of you, and she just wants to just be with you all the time. I could carry her to class and put her on my shoulder and walk do whatever all day long, and she'd just stay right with me and just be like, "Oh, this is great," you know. And I'm like, "Get away! I'm so sick of you." This cat, oh, just such a needy cat. You know, that's like, you know, being in a relationship and they're so needy, you know, it's like, get away. Just leave. The relationship's over, you know. So I'm done with this cat, but you know, I still have her. You know, once you adopt them, you know, at the Humane Society, yes, they're yours. You know, yeah, I guess, you know, what are you going to do? Kill it? I've thought about it. You know, traveling down the road at 75, 80 miles an hour, I'm just like, cat's just all over you. You're like, you know, all I have to do is roll down this window and pitch this cat out. Just push it out the window, you know. I won't have this problem anymore. A cat will just go, poof, end. You know, and it'd be so fast. He wouldn't even, I mean, she wouldn't even know. It'd just be like, what? It'd be dead so fast. Anyway. I've yet to do that. I have given it some consideration, I will tell you. I'll be honest with that. Anyway, so if we have a positive ion, we specifically call it a cation. Now, this is a negative ion specifically. That would be referred to as an anion. Anion. Okay. Now, some of you are, I don't know, chatting a little bit. Probably you're asking those around you some questions. Just ask me, yeah, if you would please, because like I say, the chatting thing, if I can hear it, that means other people can hear it. It doesn't disturb me personally. You could strip off butt-ass naked and go running around the room just screaming your head off. That is not going to disturb me in the least. It doesn't affect my life. It doesn't affect my paycheck. It doesn't affect my life at all. It is going to affect other people in their education. So that's what I have to be careful of. Not me. You know, I've already got my diploma. I've already, you know, done what I needed to do, and there are others that are working towards goals, and I want to protect that and make sure they can reach that as far as this class is concerned. So, you know, if you have questions, ask me. That would be great. And if you want to run around naked, that's cool too. I'll just ask you to go outside and do that there, screaming your head off. Sometimes don't you just feel like doing that? I mean, really? Yeah. You know, I have to have a place outside where I can just be butt-ass naked, you know? Just a place outside, hang out in the sun and just kind of just absorb the sun, you know? I just am one of those people, you know. I don't walk around the house naked like some people do. I can't do it. I'm like, can't do it. I just don't feel right. But when I'm outside, I don't want to wear clothes. Inside, I'm like, yeah, I can't be naked in here, you know. Outside, sure, that would be natural. I don't know. That is a bit awkward. Okay. So, if you ever see that in the paper where I've been arrested for you know, being butt-ass naked outside, you'll understand. Or not. Somebody have a question? Did I scare you? Okay. I don't want to scare you. I'm not a scary person. Did you have a question? Okay. Well, okay, you've got 3 positive charges, 3 protons, each are positive. And I had 3 negatives. I had 2 in the first shell, electrons, which are negative, and then 1 in the third, but I lost it. It went over there to fluorine and just grabbed it, stripped it off of this lithium. Okay. Well, it depends on what you're working with. Sometimes you share electrons. But see, if I had shared this blue electron with this one right here, this shell would not have 8 in it, so that wouldn't actually be filled. It wouldn't work. You have to have filled outer shells of all atoms when you're doing bonding. So if you're sharing electrons, make sure that the atoms have filled outer shells. I mean, that's the bonding rule. You have to do that. If you share it here, it wouldn't work. So the only way this is going to work is strip that 1 electron off, pass it of fluorine, but again, fluorine is very strongly electronegative. It'll grab it. Natural event. So that leaves me with 3 positives and only 2 negatives. So I put 3 positives and just 2 negatives. And a positive negative, that's neutral. They neutralize. They cancel each other's charge. So you're just left with a positive charge. That makes sense? Okay. You work out a lot. You've actually got some biceps there. You're scaring me. Now I'm the one. I'm the one that's scared. Chicks are starting to, put on biceps, look at me like I can kick your butt, brother. Aww. All right. Any other questions on this? Look, it looks like some of you are a little bit like, what the hey has he done here? All of a sudden, the world has flipped a bit. That's okay, Did you have a question? Yeah, because if you use a negative, again, you have equal number of protons which are positive and electrons that are negative. So if you lose a negative, you're going to obviously have now more positives. If you have equal number of positive, negative, protons, electrons, and you lose one of your negatives, you're going to have more positives. You lost one of your negatives. They were equal. You lost one. That makes you more positive. If I pull an electron off and throw it out there, I'm now more positive. Sure. Yeah. But then you could also use the term ion, so that's either positive or negative. These are both ions. This one happens to be positive, and that one happens to be negative. So if you're specifically naming a positive ion, that's cation. It's still an ion, but specifically it's a cation. This one is negative, the fluorine. You gained an electron, so obviously you have more negative charge. You gained an electron. If I pass you an electron, you're going to be more negative charge. Have more negative charge. You would. So that would make you negative. You can do this all the time. I used to do this with my niece and nephew. I'm called the balloon man, and they both remember this really well. Because when they're this big, I don't know how old that is, but it's when they're this big, that I do this. And both of them went through this period. Now, I do, at certain periods of their time, there are certain activities I have to do as they grow and get larger. There are certain things that I expose them to. Never me naked outside. Okay. However, when they're this big, what I do is I take these balloons and I blow them up, and then I rub them really, really hard, so like on my head, and it takes the electrons off my hair. Because you can strip electrons off. Like I said, those are easily manipulated. You can take them off, put them here, take them off, put them here. You can move them about. But so if I rub a balloon on my head, you may have done this really strongly, what's going to happen, I'm pulling the electrons off of the atoms. Hair's made out of atoms, obviously. Pulling the electrons off, and they're going onto the balloon. Well, that makes my hair positive because I pulled the electrons off of the hair. And they went to the balloon, which makes it negative. Now my head is positive and the balloon is negative. So the balloon sticks to my head. So I can put several balloons on my head. I can put several balloons on my arm. I can put several balloons all over my body. And then I turn on music and I dance around like a crazy person. And when they're this big, they think that is the funniest thing they have ever seen in ever. And so they always remember, oh yeah, I remember when you did the whole balloon thing, But my point in doing that is I hope I spark a little bit of interest. How does that really work? What's going on there? I mean, you have to be a little bit curious about how does that work, not just that is funny, to a person that age. But hopefully just a little spark happens there. And they're just like, well, I'm not sure how that works. And they may not think of it at that age, but when they get a little bit older, they'll be going, what happened there? And they'll find the answer to that at some point. And that's why I do those things. So I do different things at different stages of life to spark curiosity. And that's why I do those. Plus, it's fun. I do enjoy having a good time. Oh, let's not get out of this just yet. Okay, so this is an ionic bond. This lithium has positive charge. This fluorine has a negative charge. Again, one extra negative. You handed is a negative. It's going to have an extra negative. It had 9 positives, 9 negatives, but you just handed it one. So now it has 10 negatives. The others cancel. You're left with a negative. So the fluorine is negative. You had 3 positives and 3 negatives on the lithium. You lost one of the negatives, electrons. So you have 3 positives and only 2 electrons, 3 positive protons, 2 electrons, and so that leaves you with an extra positive charge, 3 positives and only 2 negatives. So the lithium is positive, the fluorine is negative. So what happens, this negative and this positive attract. They're attracting to each other because there are different charges. So that attraction of ions is what they refer to as an ionic bond. Just ions, different charged elements attracting together. It is a bond. It's not as strong as a covalent bond. Covalent bonds are the strongest. Ionic bonds are a little bit weaker. And then when you get into hydrogen bonding, like we did with water, bonding with water, that's the weakest, very weak. So ionic bond at this point. All right. Pretty cool. Yeah, you're right. Lithium fluoride. Yeah, you ended in IEE. Again, you couldn't share it. Like I say, if you shared that one electron with this electron here, okay, if those two were being shared, then you would only have 2 electrons. If we share the black one with the blue one, and these lines cross, the outer energy shells cross, and you're sharing 2 electrons, that would fill up the outer shell of fluorine over here, but it would not fill up the outer shell of lithium. Lithium would have 2. It needs 8 to be filled. So all atoms have to have filled shells to be stable, and it would continue to react until it was stable. I mean, you make a compound that's not stable and turn it loose in the environment, it will continue to react until it is stable. Got to have all outer shells completely full in order to have a stable molecule or compound. Absolutely. And if they're not, it will continue to react until they're all full. Outer shells are full. That's just a rule. That's how it works. These are ionic compounds, and obviously you got 2 different elements, so it's a compound. And ionic compounds typically are called salts. That's what a salt is. It's an ionic compound. So lithium fluoride is a salt. Not what you have at home in a salt shaker. I don't think there would be any problem that I'm aware of in putting lithium fluoride on your food. It's a salt. Potassium chloride, for people who have incredibly high blood pressure, may recommend that you buy potassium chloride. Potassium loses a 1 electron over to chlorine, which picks it up. And of course, they're both ionic then and attract. And so you can buy it at the grocery store, potassium chloride instead of sodium chloride. And it has a little bit different flavor, but it still tastes like salt. I think my mom eats a potassium chloride or uses that. She's pretty much a health nut. I mean, she exercises every day, works out in the weight room. She's 78. Works out in the weight room, and then she works out on machines, and then she walks every day, and then she eats perfectly healthy, perfectly healthy. Keeps her mind very active, travels a lot, which they say is very important as you get older. Plays bridge with friends. very, very active, and that will extend your life incredibly. So she knows what she's doing. She's researched it. She's not a ditzy woman by any stretch of the imagination, um, and I admire her completely. I hope someday I could even be half the person she is. I mean, even a quarter of the person she is. She's phenomenal. Um, but I like to have too much fun, party a little bit, drink a little bit, uh, just have fun. So she doesn't. She'll have one cocktail and she's done. You know, she's pretty wasted on that one because that's very seldom she'll have one. I'll see her drink a margarita and she's kind of staggering a little bit. I'm like, "You okay?" "Yeah, I'm fine." Fall, break a hip. Like, "Sorry, Mom." I didn't mean for you to be in a wheelchair the rest of your life. With one margarita. Oh man, should watch me. What was it? Last semester, I'll tell her myself. I don't mind. I don't have no problem. Oh, that battery's dead, so I can tell her myself. I have no problem with that now. Last semester, I got so drunk, I was trying to get out of a chair, and I fell on my face. Seriously, right on my face. It was the weirdest thing ever. It's like one moment, you're so wasted that next thing you are face against a basically patio, and you're going, "Man." I put my elbow on the chair. I had the places left aren't. Anyway, it was metal, and I was trying to push up with that, and my elbow slipped, and I was already pretty close to the floor. It cut me up, getting all the way there, and bam, and this floor, my face was wrecked. Looked like I'd been in a bar fight or something. And I told the students that I did, I told my students at the time, I said, I think Mom will outlive me, and that's quite all right. I have no problem with that. In fact, I don't know. Sometimes I hope she does. Okay. So here you have sodium. Sodium has an atomic number of 11, so you have 11 protons and 11 electrons. 2 in the first shell, 8 in the second shell, 1 in the third shell. 2, 8, and 1. And it tells you that in the upper right-hand corner of that little box for sodium, which used to be called natrium. That's why the Na symbol. Okay, now chlorine has 17 protons and 17 electrons. So for electrons, 2 in the first shell, 8 in the second shell, that gives you 10, and then 7 for that third shell. Well, you need one more to fill up chlorine. And if you notice, chlorine is way over there in the upper right-hand corner of the periodic chart. Way over there, it's very electronegative. So it can strip that one electron off. If I shared that one electron with this one, that's only give me 2 for the outer shell of lithium. For sodium. If we shared the electron on sodium with the electron from chlorine, chlorine would have 8 if we're sharing them. But if we're sharing, that only gives me 2 electrons for sodium. So sharing isn't going to work. It won't work doing a covalent bond. But if you strip that electron completely off, move it over to chlorine, that's going to to then leave the second shell as the outer shell, which has 8 on sodium. That's filled. The third shell for chlorine would have 8. It's filled, and so it's stable at that point. Well, if I lose 1 electron, I have a total of 11 protons, 11 positives, and 11 electrons, 11 negatives. And if I pull 1 off, that only leaves me 10 negatives. So at this point, by removing that, I will still have my 11 protons, but I'm only going to have 10 electrons. So I have 11 positives, but I only have 10 negatives. That leaves me with 1 positive charge. So sodium would be a cation. It's positive. And then chlorine, you had 17 positive protons and you had 17 negative electrons, but if I gain 1, that gives me 18 negative electrons. So it would have 17 positive protons and 18 negative electrons. I have 1 more extra negative electron. So chlorine obviously would carry with it a negative charge. That's salt. That's basically how that works. Sodium chloride. And that's something that, you know, we all use, need, have to have it to function. That's what it would actually look like. When it packs together, it really forms a perfect cube, absolutely perfect cube, which is pretty cool. Okay, hydrogen bonding, we have talked about that. When you have water, because it is polar, so let's again look at that. The oxygen attracts the electron from a hydrogen, leaving the oxygen partially negative and the hydrogen's partially positive. And so water will attract to other water molecules because they're polar. So if we have another water molecule, the oxygen again is partially negative and the hydrogens are partially positive. So we basically have the attraction of the hydrogen from one water molecule to the oxygen of a second water molecule. So this is not a hydrogen bond right there. That's just a covalent bond between oxygen and hydrogen. But if you have these 2 molecules attract, which are polar, that would be the hydrogen bond. Many times on a discussion question, some people will say, you know, this right here, that is a hydrogen bond. Well, it is a hydrogen bonded to an oxygen. I do understand that, but it's not what you call a hydrogen bond. You have to have a molecule, which is polar, attracting to another polar molecule. And hydrogen has to be involved in that bonding. So this, obviously, you have partially negative oxygen, partially positive, that's polar. Same, a different water molecule, partially negative oxygen, partially positive hydrogen. You know, so the partial positive of one water molecule, which is the hydrogen, is going to attract to the oxygen of the second molecule, which is partially negative. So we do get an attraction there, and that is the hydrogen bond. But, you know, and they're very weak. Like I said, the weakest of all the bonds, but when you add up, if you have a glass of water, all of the bond energy that you have just in a glass of water is actually it is very tremendous, because there is energy associated with all bonds, and that's what you do when we try to extract energy from molecules, which we do. So like we eat sugar and we extract energy from it. We get energy from it by actually breaking bonds and forming bonds. I mean, that's how you do that. And I can show you how that works, which is pretty cool. So here you have one water molecule that's attracting 1, 2. You got 4 attracting to the 1, which is pretty cool. Anyway, so there are lots of hydrogen bonding in a glass of water or a beaker of water. That's what you have. Okay, we can stop with that. You guys, it's actually 5 till. So take at least 10 minutes let's say 15 minutes, so 10 after 12.